if I can color the vertices of this graph with 4 colors in such a way that no 2 adjacent vertices have the same color. Alright, so this is called a map coloring or a graph coloring. And of course, we can do it. The same solution that worked a second ago will work here, but now I'm really only considering the graph itself, and like the way in which the lines are drawn is totally irrelevant. Alright, so this is a graph which can be colored in 4 different colors, and so like there it is. Get it? Alright, so this process of converting a problem about regions into its corresponding graph sort of gave rise to this notion of duality, which we've already talked about with polyhedra. And basically what it says is, take any graph, you can construct the dual of that graph by placing a point inside each region and connecting the 2 regions if the regions share a border. Alright. So, yeah, we can do it here, and we have to be a little bit careful because as soon as we start talking about regions, we're no longer just talking about the graph anymore, we're actually talking about the geometry of the situation. And so the particular planar embedding that you use is relevant. For example, the example from the book, here are 2 graphs. And we got a bit of this. And here is another graph, and yeah. Okay, what can we say about these 2 graphs? They are isomorphic. Or alternatively, you can just say these are 2 separate embeddings of the same graph, which is kind of like saying the same thing. Okay, but do they have the same number of regions? Actually, maybe they do. They do have the same number of regions, but the regions are like legit different. For example, can you see a property that one has that the other one doesn't? I actually don't.
Like the circle is bordering the square.
Yeah.
And then it's like not in the right one.
Okay, sure. Yeah, I guess that is kind of different. Okay, so I hereby define the dual graph. So this is a particular embedding. This is a particular embedding. What's the dual graph? The dual graph is one in which you place. What's up? Good. He said wait, but then he didn't say anything. Okay, good. I will put a vertex somewhere in each of these regions, and the outside one counts as a region as well. And then we connect 2 regions if they have, if they share a border. Okay, so do these 2 regions share a border? Yeah. In fact, they share 2 borders. Agree? Yeah. Do these 2 regions share a border? The loop and this where I am now. Yeah. So we do a little both. Am I doing this right? Sure I am. Good. What about the outside region and the square? Do they share a border? Yeah. In fact, they share 3 borders, right? Because you can exit via this door, or via that one. Yeah. What else? Does the outside region share a border with the triangle? Also, yes. So we got a bit of this. Also, what about this guy?
It's like a self-image.
Yeah, right? This is like a door. I don't remember what stupid analogy I used when I talked about this last week. But like, right, you step in through some sort of like door and you enter a new region, but that region is like the same region, right? It's like a rebirth.
Step into a door and come back in the same room. It's like a door in the middle of a room.
It's like a door in the middle of the room, yeah, that you step through, yeah.
Why would
good.
you do that?
Alright, so I believe this is like good. Anyone have any objections? I have no objections. Looking so wonderful. It's kind of ugly, I mean that might be an objection. Yeah. So notice that I added an edge through every other edge. So this red graph is the dual graph. Is that, there it is right there, right? Yes. Exact same thing. Ours is a little prettier than theirs, right? Yeah, good. Yeah, good. Okay, let's do, 3 minutes left. Let's do it over here too. So again, I place a point in every region. 1, 2, 3, 4 regions. So 4 points. And now, let's see. I got a bit of boom, and I got a la la la, and a la, and a la, and a la, and a
Yeah, that is 2 more.
and I get a bit of this. And a,
No,
that's wrong.
You have 2.
Didn't happen. What am I supposed to be doing? Okay, this goes here, and this goes here. Good? Yeah, so I believe these graphs are just not isomorphic, these duals, right?
Yeah, because the vertex, the self loop has different degrees.
Yeah. The 1000.
Yeah. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Yeah. So this is the right. So the language here is a little bit vague. Anyway, these dual. This is the dual. All right. Good. So do you see how I can convert the problem of coloring regions into just coloring a dual graph? All right. And let's just go through this. Let's just spit out this kind of term right now. The chromatic number of a graph is the minimum number of colors needed to color the graph such that no 2 vertices share the same color. Alright, so let's do it. Let's go. Oh, we have like 2 minutes, right? So let's just draw some happy graphs. So here's a happy graph, and here's another one. Maybe no. I think I have to define this only for simple. It's irrelevant, right? If it's simple or not, because all that matters is whether the 2 vertices.
Mr. That's a multigraph.
Right. Yeah, but I think it's irrelevant because good. Oh, but you can't have any loops, otherwise it's just impossible to do. So anyway, just real quick, before let's just add one more, just for kicks. How many colors can I color this graph with?
3.
3, say all the people. Yeah, I think that's right.
4.
What should I do? Put green here. Can I do it in less than 3?
No.
No, because these 2 need to be, yeah, of course I cannot do it in less than 3 because I have a K3. Yeah, so I need at least 3, but then this one can be blue again, and then this one can be anything. Alright, so we say that the chromatic number of this graph is 3. Good?
Yeah.
Alright, good. Some homework due tomorrow on dual graphs and colorings. That was not the greatest lecture ever, but good enough. Goodbye, people.